Importance of negative examples for audio-visual sound separation, which will be presented by Scott Wisdom.
Okay. All right. Thanks so much. So yeah, I'm presenting on behalf of my co-authors, Themios Zenas and John Hershey, who we'll be hearing from in a little bit. Um, so as the title of this talk suggests, the task we're concerned with here is audio-visual on-screen sound separation. The idea is we have a microphone observing some audio mixture, and we also have a camera observing the scene. And our goal is to extract the sounds only of objects that we can see on screen in our camera. So in this case, the goal is to recover the voice of the person in the red shirt and the dog, and reject the sound of the wind noise and the person in the green shirt. So we've proposed an approach for this problem called audioscope, which can actually be trained entirely unsupervised on in the wild data. Version 1 of this was at iClear, and version 2 is here at this conference. We have a poster on Thursday if you want to check it out. Our approach is sort of unique compared to a lot of other audiovisual separation approaches in that we first do audio-only separation into some number of sources, and then we use audio-visual attention between the separated sources and the input video frames to get a probability for each source that it originates from an on-screen object. And then we can just create an estimate of the on-screen audio by using the probabilities as mixing weights across the sources. So I don't have time to go into all the details of this, and John might talk about it in a little bit. What this paper is mainly about is how to evaluate these audio-visual separation models. So the usual way that audio-visual separation models are evaluated are using what I call positive examples. And positive in the sense that we start with a video that is on-screen only. So it's a video where all the sounds originate from on-screen objects. We add some interfering audio on top of that, and that gives us an example to evaluate. We run that through our audio-visual separation model, and the goal is to recover that original on-screen audio. And we can measure the quality of that reconstruction using something like signal-to-noise ratio. However, what about this interfering audio? How well do we do with sounds that are not on screen? And so to evaluate audioscope, we've also used so-called negative examples where we have videos that have only off-screen audio. And the way we did this in our audioscope papers was we took videos that were labeled by humans as only containing sounds that come from off-screen objects. We add some additional interfering audio to match the distribution of those positive examples I mentioned on the last slide. Run that through our separation model, and in this case, since all the audio is off screen, ideally we'd like the output of our model to be 0. To measure the quality of this, we define a metric called off-screen suppression ratio, or OSR, which is just the ratio of the input power to the power of the estimated on-screen output. And what is interesting is there's this trade-off between SNR of reconstructing on-screen sounds versus the OSR of rejecting off-screen sounds. And so with our particular model, we can tune this scalar bias on the logits of our on-screen probabilities for each source and trace out these interesting curves that show this trade-off between SNR and OSR. And so what we propose is models, after they're trained, end up with these sort of arbitrary operating points in terms of OSR and SNR. It's rather hard to compare these different models to each other. So we propose this calibration scheme where you can tune this bias such that all models achieve some target OSR, and then you can just directly compare their SNRs in terms of their quality. And in this paper, we also consider some other types of negative examples. One case is so-called replace video examples. So in this case, we take a single on-screen video, we just replace its video frames with the video from another video, and then we can measure OSR. Of course, in this case again, since all sounds are off screen, we want the output to be nearly 0. And thus we want to maximize OSR. One other version of this is we can just blank out the video frames too. So these are also single videos, and we're just measuring OSR. And so we can compare two versions of our Audioscope V2 model, an unsupervised version and a semi-supervised version, which is trained on not only our unlabeled data, but also some labeled examples. And if we're only looking at the SNR and positive examples, we would say, oh, well, the SNR for the semi-supervised model is going down, so it must be worse. But if we look at the negative examples, the story changes. The SNR of reconstructing that off-screen audio is now lower, which is good, and the OSR, which is rejecting the off-screen sounds, is higher. So what we can see is that our semi-supervised model is actually more robust at rejecting off-screen sounds for these types of negative examples. And just to give kind of a qualitative illustration, these are the outputs for the unsupervised model on the left and the semi-supervised model on the right. What we're looking for is that these probabilities are low for the negative examples, which so you can see that these probabilities are lower for this semi-supervised model compared to the unsupervised model here. Again showing that this semi-supervised model is more robust. So thank you so much, and thanks for your attention.